Hey everybody, Mr. Zone here. So let's keep talking about our sound and waves unit. This is unit 3, lesson 7, and we're gonna actually focus on sound now, finally. So the whole point of all that wave discussion we've been talking about so far is so that we can actually think about sound. Remember, sound is a longitudinal wave. Remember, it's the air molecules going back and forth. They squish a little bit, and then they rebound, but then overshoot, and then rebound, and overshoot, and continually forever. And well, except for late damping, sorry, where it slowly goes away. So we want to actually talk about sound and some of the features of it. So the first thing we want to talk about today is the speed of sound, and the speed of sound is relatively, it's pretty fast, right? It's about around 330 meters a second. It is 332 meters a second at 0 degrees. It is temperature dependent. So you can think about it in this way. It takes about 3 seconds for sound to travel a kilometer. Right? So it's pretty quick, but it's not that quick because you can actually see this, or sorry, you can hear this if you hear an echo. An echo is the sound leaving, let's say if you clap, and hitting a flat surface and bouncing off and coming back to you. So it has to travel that distance, and the time delay between when you hear it close to you and when it bounces off something, we call that an echo, and it depends on the speed of sound. Right? So because the speed of sound is not very quick, we can actually hear those echoes. Now, the thing that I want you guys to learn about today is the temperature dependence of it. We're going to use a linear model here that uses 0 as our starting point. So it's going to be 332. That's the starting point. Or like a y-intercept in a y equals mx plus b formula. And the slope is going to be about 0.59 meters a second per degree Celsius. So that means every degree we increase the temperature, the speed of sound increases by 0.6 of a meter per second. Right? So every 10 degrees, the speed increases by 6 meters a second. Right? And that's because of the way that when you increase the temperature of the air, it becomes less dense, easier for the sound to move through it, so the speed increases. All right? So this is our formula here for the speed of sound you're going to need to know. It's just interesting here because we can use this for lightning. You see lightning flash, and then we hear the thunder rumble a little while later. Or if it's very, very close to you, they're almost simultaneous. And that's because lightning, the image that we see, the flash, travels at the speed of light, which is about, sorry, it says 3 times 10 to the 8. Sorry, 3 right there. It's 3 times 10 to the 8 meters a second. We call that c, the speed of light. So that's, what is it, 1,000,000 times faster than the speed of sound. So when you see the flash of light is almost instantaneous between when it happens and when it gets to your eyeballs, but then the sound takes a little while longer. So you can tell, for a simple way that you can tell how far away lightning is you count the number of seconds and then divide by 3, because every 3 seconds represents 1 kilometer. So if I count 9 seconds, I know that the lightning struck the ground, or happened. It didn't strike the ground, it was just between clouds. It was about 9 kilometers away. And you can use this to keep yourself safe, when you're out and there's a thunderstorm. Okay? Let's do a quick example here. So what is the speed of sound today? So currently the temperature, as I'm writing this, is about 14 degrees Celsius. So what is the speed? What is the speed of sound at that time? So, whoopsies, let's go back here. So the speed is going to be equal to, we said, 332 plus 0.59 T. Now that's a capital T for temperature. So that's going to be 332 plus 0.59 multiplied by 14, which comes out to approximately 340 meters a second. Okay? So that is the speed of sound outside right now. Okay, pretty straightforward little problem. Now, speed of sound is not the same in different materials. Different materials have different speeds of sound. For example, solids is about 10 times that of air. Speed of sound in steel is about 5 kilometers every second. Very quick. You can actually hear a train coming through the railway tracks before you can actually hear the actual train engine. Okay, so you can use the railway tracks actually transmit the sound of the train coming prior, because it travels so quick down it. Just a quick little anecdote. When I was in physics, I heard of a teacher who would actually hit the railway tracks. You'd see him hitting the what's it called, the railway tracks with a sledgehammer, and you'd actually hear it going through the railway tracks. The police may have been called at one point. So anyway, now an interesting one is the speed of sound in water. It's approximately 4 times as fast. So if ever you're underwater and you hear a boat coming, you can actually hear it coming a lot sooner. It sounds as though the boat's on top of you, especially if you're underwater. It may sound like the boat's right on top of you, but it's actually quite far away. And that's because the speed of sound is so much quicker in water. It's about 4 times as fast, approximately 4 to 5. Okay. And here, this is the one we were talking about, air. Air travels. That's 332 meters a second at 0 degrees. All right, so I'm going to put this table here on our Weebly, so you can reference it if you need to. Now, the other one thing we want to talk about is the intensity of sound. Now, the intensity of sound is, basically how loud is the sound. Okay, and the way that we can think about this, there's 2 major features before we even talk about this decibels scale. The 2 things that define how loud something is the source strength. Right? If I increase the volume on my speakers, or if I play my trumpet louder or something like that, you get a louder sound. And the other one is distance, because we know that sound emanates outwards. So the farther it goes, the larger the area is that sound wave has to cover, and it decreases. And we're not going to worry too much about these things, but we're going to talk about a way that we can measure that. And the reason we use something called decibels, and the reason we use it is because we can use it as a logarithmic scale. Now, you probably haven't seen these before. You've probably heard about them before, but you've never actually dealt with them before. We use log scales when we need to deal with a very large interval of measurements, a large amount of orders of magnitude. So, for example, another one of these logarithmic scales is the Richter scale for how strong an earthquake is. And the reason we use that is because we're actually looking at the exponent. Let's talk about this for a second. So the threshold of human hearing, the lowest that we can hear, is 10 to the negative 12 watts, so joules per second, per meter squared. So that's the lowest that the human ear can hear. And we're going to call that 0 decibels. Okay. Now, every time we go up by 10 decibels, that's going to be a change of 10 to the power of 1. Okay. So this is a log scale. Every time you go up by an increase of 10, we're actually multiplying by 10 instead. Okay, so we're looking at this as a ratio, and then a log of that ratio. So we're looking at what these logarithm do is it takes out the exponent. So if let's say if I use my calculator and I just type in log of 1,000, that's going to give me the number 3, because 1,000 is 10 to the power of 3. See how it takes out the exponent, right? Now it's a measure of comparing it to the reference. This is a little bit complicated. When we do an example, it'll make more sense. Now it is multiplied by 10 because this is a decibel. A bell is its own unit, named after Alexander Graham Bell, the guy who invented the telephone. But we're talking about tenths of bells, because one bell is actually, the difference in one bell is actually quite a lot, so it's not a very useful unit. So we use decibels instead to see the difference there. Okay. So let's use an example. This is probably a little bit complicated. I haven't done a very good job explaining it. I apologize. So let's see what we can if this table helps us out here. So in this table, you can see when we have 10 to the negative 12, that's our 0. Now if you go up to 10 decibels, that's 10 to the negative 11 watts per meter squared. Now if we go up to 20, so this is now if I go from 0 to 20, I've increased by 20 decibels. That is an increase here of 100, or 10 times 10. Okay? So anytime I go up by a power of 10 here, by multiplying by 10 again, I'm increasing the decibels by adding 10. Okay? So what is interesting here, threshold of pain is in the order of 120, 130. That's where sound starts to actually hurt our ears. A normal classroom is between 50, 60, 70 decibels. Cars going by or things in the 90, 80, 100 decibels. 160 decibels, that's when your eardrum pops. Okay, and there's actually a limit to here. Once you get in the order of past this, like you get in the 200 decibel region, we reach what we call a shock wave, where sound no longer behaves like an oscillator. It doesn't go back and forth. The sound actually produces a shock wave, an explosion, for example. An explosion is basically sound that's so loud that it no longer allows the air to react in a sort of oscillatory way. It doesn't let the air bounce back. It sort of becomes a shock front, and it travels as an explosion. Okay. So the important point is, if we go up by 20 here, that's an increase in 10 to the 2. If I go up, let's take another one. Let's go 50 to 80. Let's say that's an increase of 1,000, because that's an increase of 30 decibels. 30 decibels, we divided it by 10, that becomes 3, so that's 10 to the power of 3. Okay, that's how the decibel scale works. Every time we go up by 10, we're increasing by a factor of 10. We're multiplying by 10. So let's try an example here. So let's say we have a sound. It's 100 decibels, and it's 1 meter away. I'm 1 meter away from a sound, and I'm measuring it with a sound meter, and it says 100 decibels. It's quite a loud sound. It's like a guitar amplifier at close range. Okay, quite loud. But I go 100 meters away, and now I'm measuring that sound as 60 decibels. How come? Why did the sound go down from 100 decibels to 60 decibels when I increased the distance? Okay, so let's think about it for a second. 100 to 60 decibels. So what's the difference there? 100 minus 60, is 40 decibels. Okay, so I have a 40 decibel difference, which means what? How much difference is there in sound then? So 40 divided by 10 is 4. So that means it's a difference in sound strength by 10,000, which is 10 to the 4. Okay, it's 10,000 times quieter. That's what the difference between 100 decibels and 60 decibels is, a difference of 100,000 times. Now, where does that 100,000 come from? Now, let's think about sound. Remember, sound is going to be emanated from source, and it's going to come out in some sort of a sphere, right? And then this is the sphere of influence, let's say, for my sound, and that's at 1 meter here to begin with. But once it gets to a much larger distance here of 100 meters, that sphere has gotten much, much, much bigger. And how much bigger has it gotten? So this area of a sphere is 4 pi r squared. So if I change this area to 100, that's going to be 100 squared. So 4 pi 100 squared. So that's going to now be my new area, let's call it A prime, is going to be my initial area, A, multiplied by 10 to the 4, 10,000. Okay? So because my sound has expanded, has gotten so much bigger, that wave front has gotten so much bigger, it's decreased its intensity because it's stretched out. Think of it like a balloon. As you take a balloon, you blow up a balloon, it becomes thinner. The material, the latex, gets thinner and thinner and thinner as it gets bigger and bigger and bigger. So same idea, the sound wave expands and it gets thinner and thinner and thinner, and it decreases, the area increases by a factor of 10 to the 4, so its intensity decreases by a factor of 10 to the 4, and 10 to the 4, that 4 here means a difference in 40 decibels. Okay? So 40 decibel difference actually means a sound intensity difference of 10,000, which is quite a lot. And that's why we use the decibel scale. We don't see much, our ears don't register much difference between, let's say, 70 hertz and 60 hertz, 70 decibels and 60 decibels, but it's an order of magnitude of 10. Okay, so these are huge differences, and we have this huge range of data that we have to cover. So instead of using just a regular linear scale, we use logarithmic scales to help us analyze these things in a more useful way. Okay, so that's all we're going to do for today, in this lesson at least. So we're going to do speed of sound and intensity of sound. Okay, so here's some problems I'd like you to work on. Pretty straightforward, using our velocity formula, our speed formula for 7.3 set questions, and then 7.4 is just looking at playing with these using these log scales. Now this B here, that's an actual bell. Okay, so 10 decibels is 1 bell, named after Alexander Graham Bell again. All right. Okay. So try these problems and have fun. All right. So Mr. Stone signing up.